Hey, welcome to all of you on my YouTube channel, that is JE Physics Maniac. Now we will start the class 12 series for JE preparation for main, advanced and NEET courses. Gradually we will complete all the portions. So without wasting much time, let us start. So we'll start the first chapter in class 12th portion, that is electrostatics, and we will cover only the things which are productive for the JEE examination. So let's start. So in electrostatic, the first portion that we'll study is properties of charges. This is a theoretical aspect and we have to know it. The first property that I will write here is that a body with finite charge must have mass in it. It's a very significant property. It means what? That means we cannot get a body which is having zero charge and its mass is also equal to zero, right? You can get some cases where a particular material is electrically neutral. That means it has equal number of positive charges as many number of negative charges. I'm not talking about those bodies. I'm specifically talking about those bodies where it doesn't have any existence of charge in it itself. For an example, I will take the case of photon, right? I can take another example also, neutrino. For both these bodies, whether I talk about photon or I talk about neutrino, for both these bodies Q is equal to 0, and as Q is equal to 0, for photon we can check that we know that the relativistic mass is given as m equal to m naught by root under of 1 minus v square by c square. And since photons travel with the speed of light in vacuum, so we can write v is equal to c. If I put v equal to c in this equation, I will get m naught is equal to 0. So you can readily check that the photon was having zero charge as well as rest mass is equal to 0. So that's one of the property that we have to remember. Second property is also a very interesting property, that is that the charges are relativistically invariant. What do you mean by this? Just before some time I have written one formula that you can see here, that m is equal to m naught into 1 minus this. So in this case I can clearly see that if a particle is moving with a speed which is comparable to the speed of light in vacuum, its mass will vary, right? But in case of charge, that even if you take a charged particle, suppose it is having a charge plus q, it is traveling with the speed of light in vacuum c, the charge on the particle continues to be q. So there is no change in the magnitude or in its sign. So that's why I said the charges are relativistically invariant. In the scope of study for JEE, we will not have much consequences of this particular property that we have seen, but in the higher studies we will see that it has some adverse effect, right? Okay, so two things I repeat once again. One property is that a body which is having existence of charge must have some mass, and second is the charges are basically relativistically invariant. That means even if a charge is moving with constant velocity, acceleration, or with the speed of light in vacuum, then there will be no change in its magnitude or in its sign, right? Okay, now the next thing that we'll go into is conservation of charge. So basically the nature will always show its wings in different colors in terms of conservation of mass or charge or energy at different times. So let us know what is conservation of charge. In conservation of charge, I should write that the total charge of an isolated system is constant. That means it remains conserved. So here I am specifically talking about total charge, and that too of an isolated system. What do we precisely mean by this term isolated system? It means that it is not in contact with any other subsystem with which it has a tendency or it has a chance of leaking charge to the surrounding, right? So that means here I can write Q total, that is for an isolated system, that is equal to constant. If we take two conducting materials, let us say it is having charge Q1, we can have another conducting material of charge Q2, and the initial charge of this system we can comfortably write it is Q1 plus Q2. Now if they are connected with a wire, the charge separation will take place, charge flow will take place if they are connected with a wire. So now finally, after steadying down, the total charge of the system will become Q1 plus Q2 irrespective of the individual charge holdings of conductor 1 and conductor 2. So that's what we wanted to mean. That means if I consider this Q1 and Q2 as a single system, for this single system total charge initial is equal to total charge final. There will be no change in the magnitude of the charge held by the system. So on the right side of the screen you can see that there is an example. It's a very nice example, natural phenomena that we used to see. One is called pair production, another is called pair annihilation. So what happens in case of pair production? You can see that two gamma ray photons are coming here, they are colliding. Two gamma ray photons, this is one and this is the second one, they are coming, the collision is taking place here. As a result, electron and the antiparticle of electron is produced, which is called positron. So what is the total charge of the system? Electron is minus, positron is plus. So Q total is equal to 0. Photon is neutral. So initial charge of the system is 0. Final charge of the system is 0. It follows conservation of charge. Another nuclear phenomenon if I take, it is pair annihilation, just opposite to what we have seen now. In this case, a positron and electron will collide. As usual, minus E plus E will make it to 0. Finally, two gamma ray photons are produced and here photons is neutral. So Q final, that is also equal to 0. So we are saying Q initial is equal to Q final, right? Let's proceed. Now another very interesting property that we are going to learn, although it's a primitive idea, that is quantization of charge, right? What this idea is all about, this tells that the charge of a body, Q of a body or Q of a particle as you say, is equal to plus minus Z into E. What is a Z here? Z is an integer. That means as per this particular principle, the total charge of a body has to be integral multiple of electronic charge. E is the charge of a single electron. So what is the constraint here? Constraint here is that it is mentioned that Z has to be an integer. Now why I said it is a primitive idea, on the right hand side you can see that if you take Q is equal to N, here N is taken as integer. Now the charge of a body can be 1e, 2e, 3e, anything, but the number has to be integer. Now in physics we have this model, that is quark model, right? Basically the quarks are sub-electronic particles. Just like electron, proton, neutron are subatomic particles, the quarks are sub-electronic particles, right? It is believed to be there are 6 quarks, up, down, charm, strange, top, bottom. I am not going into the detail, but after the advent of quark model, it is seen that if I talk about up quark carries a charge of plus 1/3 of E. If I talk about down quark charge, it is minus 2/3 of E, right? So here these numbers plus 1/3 minus 2/3, these numbers are indicating that Z may be a fraction too. So it is not mandatory that this N or Z, whatever you say, has to be an integer only. It can be fraction. So that's why I said okay, it's a primitive idea, it's an old idea. All right, right? Then the most important thing, the most important incident that happened in electrostatic by this person, a great scientist Coulomb, gave the idea that what is the nature of interaction between 2 point charges, right? So first I will mention that we are going to study the interaction between 2 point charges. Why necessarily we are talking about the point charge? Remember, we are taking point charges because for a point charge only, center of mass will coincide with the geometrical center will coincide with the center of charge. So it's a very sophisticated idea. That's why we have precisely chosen it to be point charges. Or even if we take two rigid bodies, we have to take in such a way. Now this is a very important point I am discussing. Please keep it in your mind. If we take two rigid bodies, we have to take in such a way that center of mass of the rigid bodies must coincide with the center of charges. Then only we will be allowed to take the distance between the two charges as this is r. So if we just say it is the center to center distance, probably we will end up in trouble while solving some higher order questions. But we have to say scientifically is that r is the distance between two centers when center of mass and center of charge are coinciding. All right. Okay. So here are 2 point charges on this diagram. You can see Q1 and Q2. If they are of opposite sign, one is plus, another is minus, they will attract each other. That means this plus Q will attract this minus Q, and this minus Q will attract the plus Q towards it. Right. So the first fundamental thing that we have seen, we will note here, that is the forces of interaction is either radially outward or radially inward. All right. Radially outward or radially inward means what? Means along the line joining, either towards the charges or away from the charges. So they are radially outward or radially inward. Very significant point we have to remember. Okay. And there was one more observation, and that observation tells that this force of interaction, if I talk about F21 or F12, this force of interaction is basically F was seen as proportional to 1 by r square. This is seen as proportional to 1 by r square. Right? So two laws basically it is maintaining. One, it is maintaining inverse square law, and the direction is radially outward or inward. So if we club these two particular considerations together, then we can comfortably write that F12 vector is equal to 1 by 4 pi epsilon naught. Epsilon naught is the free space permittivity, and what we have to remember, that the value of 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 in SI unit. Right? So this is 1 by 4 pi epsilon naught Q1 Q2 by R12 square into R12 cap. So this is the thing. If the direction is along the plus R12 cap, we will say the force is repulsive because it is radially outward. And if the force by any chance, if it is coming minus R12 cap, then the force must be attractive because then it is radially inward. Okay, so plus R12 cap is for repulsive force, which is radially outward, minus R12 cap is radially inward, right? We can have different forms of these forces that I will slowly explain as it comes forward. So F12 vector is equal to, we can write 1 by 4 pi epsilon naught Q1 Q2 by R12 square. This R12 cap we can write R12 vector by R12 magnitude. So it will take another form as 1 by 4 epsilon naught Q1 Q2 by R12 whole cube R12 vector. So it can be of any form. I hope you understood, right? So here I can see that it can take multiple forms, whether this particular form I am taking or the other form, right? Okay, yeah. So basically we are dealing here about two equations. One is this format that I have given, and another one is this format. Okay, right, fine. If you want to take note, you can pause the screen and take the note of it, right? Next I will take a very simple example. I will take a very simple example, very simple example of interaction between two charges, rather three charges. I can see at point A and B there are two plus Q charges, and at the middle there is one small point Q charge. I want that the entire system is in equilibrium. I'm writing the entire system is in equilibrium. So when I say that the entire system is in equilibrium, I have to write that F net is equal to 0. So if I say that F net is equal to 0, what am I supposed to write here? I will write that force between A and B plus force between A and C, because the interaction between A and C and B and C is the same interaction, is equal to 0. Now you see, force between A and B, force applied by A on B is radially outward because they are of same charge. So can I write 1 by 4 pi epsilon naught? If I take this term on the right hand side, it will become minus. So F of AB will become minus F of AC. So F between AB 1 by 4 pi epsilon naught Q square by, if I take this as A, this is also as A, total distance is 2A. So 2A whole square means 4A square is equal to minus of 1 by 4 pi epsilon naught Q by S square, Q into Q by S square. See, again I will check force between A and B, 2 plus Q charges are there. So it becomes Q square by 4A square. Force between A and C, Q1, Q2 is capital Q, small q, distance is A square. So from here, the conclusion that we will get that small q is basically equal to minus of Q by 4. So that means what? That means if the system has to be in equilibrium, then the value of small q should be equal to minus of Q by 4. So one point, Q has to be a negative charge and its magnitude should be minus of Q by 4. Next question that comes in our mind automatically is, what is the nature of the equilibrium? We will study, but as of now, if the system is in equilibrium, then net force has to be 0. Net force, while I am taking, I have to take the interaction between A and B and then plus interaction between A and C, because the interaction between A and C and the interaction between B and C is the same interaction. So any one you take. All right, fine, let's proceed. We have taken another case, that is case 2 here, and you can see case 3 also, right? So what I am doing here in case 2, I am projecting a plus Q charge, small q charge, in the direction which is perpendicular to the line joining between A and B. So suppose if the charge particle is here at any point of time and I take this particular distance as y, this is a, this is also a. So can I write that at this point of time the force that will act between A and C will be in this direction along this line joining. Similarly, the force between B and C will be along this line joining. I hope it's clear to all of you, right? Because it's a interaction between two positive charges. So this force is in that direction and this force is in this direction, and both the forces will be of equal magnitude. Why? Because the charges are of same magnitude and the distance is also same. This distance is root under of y square plus a square, so as this one is also root under of y square plus a square. Now if you see the beauty of this, if I divide this force into two components, this is fx, this is fy, this is fy. For this left side force also we will get this as fx and this will become 2fy. Now on the point C, if I write, you see the forces are on the left fx, on the left fx, and in this direction the force is coming to be 2fy. So the net force along x-axis is getting cancelled, so I can write summation of fx is equal to 0. So this particle C will not have any acceleration along x-axis, and since it is having a force acting along y, so it will have acceleration along y. So in this particular case the charge particle C will continue to move along y-axis. But what happens if this charge particle is negative instead of being positive? Then if we see the direction of the forces, we will take like as we have taken in the previous cases. So here I am taking them, this is the F, this is F, right? So in the previous case the charge was positive, that's why the direction was radially outward. Now here in this case, if I take the direction as radially outward, I will be doing the wrong thing. Why? Because now the charge that I have taken here is a negative charge. So for a negative charge the force should be radially inward. So instead of taking radially outward force, I have to take here radially inward force. So here the force will be in this direction, that is F, and for here also the force is in that direction. Now if I divide them into component, as usual, this is Fx, in this direction that is Fy, for this left side force also this is Fx, and in this direction Fy, right? So here in the case also you can check summation of Fx is coming to be 0, so Ax is equal to 0. But there is a net force acting in the negative y direction, so the net force is acting along this line, that is of 2fy. Achha, so that means the charge particle when it is projected in the upward direction will feel a retardation, that means the force will act in this direction. What happens if I project the charge in this direction? Same thing will happen, because when the charge is here, force will act like this, If I take the component, you check, this is Fx, then this will be Fy, this is Fx, and this will be 2Fy. So then the charge particle will be feeling a force in the positive y direction. In this direction it will feel a force. So basically we will check later, if given a small oscillation, the charge particle will execute oscillation about the y-axis, right? So now next point that I have written, I will comment on the condition of equilibrium of the three cases that I have checked. So let us go back. In this case, this charge was minus q by 4. If you project the charge in leftward or in rightward direction, listen to me very carefully. If we project the charge in leftward or rightward direction, suppose the charge is projected towards A, can I say that the distance between A and C will decrease, whereas the distance between B and C will increase? Alright, so that means distance decreasing, A proportional to 1 by r square. So that means force between A and C will be increasing, which is attractive force, and force between B and C will be decreasing. So that means the charge particle will accelerate in that direction without any chance of coming back to the initial position. No chance. Such kind of equilibrium we call it unstable equilibrium. So I comment case 1, charge particle is in unstable equilibrium. Right? Case 2 also we have already checked. It will continue to move along y. Unstable equilibrium. Alright. And if I check, that is case 3, it is having a tendency to come back to the initial position. So case 3 will be of stable equilibrium. Right? So in our lecture, we will always play tricks and tweaks so that you are always very much concentrated. Now the tricks and tweaks is that you have to check for case 2 whether indeed it is in unstable equilibrium or not. So that is your checkpoint. So the first checkpoint I am giving to my dearest friends to check whether in case 2 the charge particle will be in unstable equilibrium or not. Right? Fine. So till now what I have studied, let us go back. We have studied about the properties of charge. Then we have studied about the conservation of charge. Then we checked what is quantization of charge, how it is relevant or how it was relevant, whether it is maintaining the same relevance nowadays or not. Then we have studied about Coulomb's law. We have seen that how Coulomb's law looks like in crude form. We have checked the interaction between two charge systems. Then I have applied in 3 cases and we have checked the condition of equilibrium also in 3 cases. So the next thing that I am going to do is detailed discussion in Coulomb's law. Okay. As you know, as you can see here, my handwriting is looking like a old Latin scripture. I hope you will take enough pen to unlock it out, and as time progresses I will to come up with a better handwriting, right? Okay, so now as we have already written, F12 vector is equal to 1 by 4 pi epsilon naught q1 q2 by r12 square r12 cap, or I have written 1 by 4 pi epsilon naught q1 q2 by r12 cube into r12 vector. So these are the two forms that I told you already, and on the basis of these two forms I will discuss very few important points. Firstly, as we have seen that F2 vector, it acts either radially outward, that is plus r12 cap or minus r12 cap, and magnitude of F12 is proportional to 1 by r12 square. If these two forms are being maintained simultaneously for any kind of force field, those force fields are called central force fields. Don't forget. So both the condition needs to be maintained. That means the force should act radially outward or inward, and second, it must maintain inverse square law. Okay, don't misunderstand or misquote me. What I am saying, just remember as it is. Force must be radially outward or inward, and it must be a inverse square variation. Then those force fields are called central force fields. So what is the net intake of that? Remember, all the central force fields, are conservative force fields. All the central force fields are conservative force fields. This is point number 1. And point number 2, I will check a very interesting and unique thing, that if I write F12 vector is equal to 1 by 4 pi epsilon naught q1 q2 by r12 cube into r12 vector. If you notice this entire term here, it is constant, right? If I may write like this, I'm sorry, this is a constant term. So I can suitably modify this to write it as c by r12 cube into r12 vector. C is a constant. Now from here, if I do r12 cross f12, you see it is coming c by r12 cube. It being a scalar, I am not disturbing. r12 cross r12, which is coming to be 0. All right, very interesting thing. So r cross f, what it indicates? It is torque, right? So what I'm seeing over here, that torque is basically coming to be 0, and we know this is nothing but a rate of change of angular momentum, right? So the second thing that we are learning out of it is as tau is equal to 0, which is equal to dl dt. So L vector is equal to constant. And here comes the thing that we have to remember, that in Bohr orbit, if you remember the force of interaction between the nucleus and the orbiting electron, that is given as 1 by 4 pi epsilon naught Z is the electronic charge into E by R square, it being an attractive field minus of R cap. So this can be written as Z E square by 4 pi epsilon naught R cube into minus R vector. Right, when I'm writing R cube, I must write R vector. So basically this electrostatic force, it being a central force, so that means angular momentum of the orbiting electron will be conserved. So that means if I precisely talk about the angular momentum of the orbiting electron, this is quantized as we know, that is L is equal to mvr is equal to nh cut, and as well as it must be conserved. So if question comes that the angular momentum of the orbiting electron is only quantized, only conserved, both quantized and conserved, I hope your answer should go for quantized and conserved, right? So that's all, my dear friends, for this lecture. In the next lecture, we will come out with some beautiful explanation or explanatory problems of Coulomb's law. Then gradually we'll move on to fields. I hope you have enjoyed. If you have enjoyed the lecture, if you have understood, or if you have learned something out of it, please do like and subscribe my channel. Thank you. Thank all. Stay home. Stay safe.